Welcome and thank you for joining. In this lesson, we're exploring how to use the first derivative to determine the increasing or decreasing behavior of a function, as well as finding the points where the function reaches a maximum or a minimum. The max and min points on the graph of a function are also known as the extreme points. Minimum and maximum occur at points where the function or the graph of a function is making a turn, and this is the reason why we sometimes call them turning points. At the turning points, the behavior of a function will change from increasing to decreasing, so from positive to negative. And at the minimum, the behavior of the function will change from decreasing to increasing, so from negative to positive. Because the behavior of the function is changing to opposite, we call the max and min the critical points, so the points where the behavior will change from positive to negative or from negative to positive. To further explore how to use the first derivative to determine min and max, which will be the focus on this section of the lesson, let's take a look at these two examples. So what we see in here is the graph of a second-degree polynomial function or a quadratic function. This function hits a minimum at x equals 1. At the minimum, as you can see, the slope of the tangent will be equal to 0, which means that the derivative will have a value of 0. On the left side of x equals 1, so from negative infinity to positive 1, the function is decreasing. The slope of the tangent is negative, which means that the derivative is negative. On the right side of x equals 1, so from 1 to infinity, the graph is increasing. The slope of the tangent is positive, so the derivative is positive. Exactly at 1, the slope of the tangent will be 0, and this is where the function will hit a minimum. So we're going to say that the derivative of the function at the minimum will be 0. In a similar way, we discuss the graph of the function described by this parabola here, which is second-degree polynomial function or quadratic function. In this case, the graph will show a maximum at x equals negative 2. On the left side of negative 2, so from negative infinity to negative 2, the function is increasing, which means that the slope of the tangent is positive or the derivative is positive. And on the right side of negative 2, so from negative 2 to infinity, the graph is decreasing, so the function is decreasing, the slope of the tangent is negative, and the derivative is negative. Exactly at the highest point on the graph of a function, the slope of the tangent will be 0, so we're going to say that the maximum has the derivative equal to 0. So considering all this, then we're going to say that at either min or maximum points on the graph of the function, or at the extreme points or turning points or the critical points on the graph of a function, the function will have the derivative equal to 0. So therefore, if the derivative equals 0 at some point x equals c, it means that the point with coordinates c, f of c will mark a critical point. Now, based on this, we build one very important theorem in calculus. So we are going to say that if a function has a local max or a local minimum at x equals c, that means that here is a local max, here is a local min. The derivative at these 2 points would be equal to 0. However, this is not the only case, or that's not the only way we can describe or identify the highest or the lowest points on the graph of a function. In some cases, the function may be continuous at the point where it reaches a min or a max. However, the derivative may not exist. So therefore, based on this theorem, we're going to say that the function has a local min or max when either the derivative is 0 or the derivative doesn't exist. So let's look into this a little bit at some more depth. So if we look at the graph of this particular function, you probably recognize that this is a graph of some absolute value function. This will have a minimum at this very corner, that's what we called it, and this will have a maximum at the corner. The function is continuous at the point where we are discussing the derivative. So at the minimum and at the maximum, the function is continuous, which means that the function has a defined min and a defined max. However, when we look into the derivative of this function, we say that the derivative at this particular point, x equals c we said, would be equal to, well, it will be undefined. The reason why is because if we were to measure the derivative on the left and right hand side, since this point belongs to both pieces, then the derivative will have two opposite values. So this is a negative and this is a positive. So therefore, we're going to say the derivative at exactly this point, at this exact point, doesn't exist. In a similar way, we reason about this maximum, so the derivative doesn't exist. However, the graph will mark a critical point or a min or a max. So another case when the function is continuous is hitting a min or max or an extrema. However, the derivative is undefined is when the graph of the function will present a cusp. So we have seen these graphs before and discussed them before. We're going to say that this will present a minimum point, this will present a maximum point. So the function is continuous at both min and max, so min and max exist. However, if we were to determine the derivative of a function at those points, which is basically the slope of the tangent, then the slope of the tangent at those points, since the tangents are vertical lines, will be undefined in value. So therefore, we're going to say that the derivative will be undefined as well. So in a similar way, we're going to say that the derivative at the maximum here doesn't exist. So we are going to say that a function can reach a min or a max when either the derivative is 0 or the derivative doesn't exist. Now, if the derivative doesn't exist but the function reaches a min and max, we also have to emphasize that the function itself is defined at the min and max. However, the derivative isn't. So to summarize this, then we're going to write that the function f of x will be defined at the critical point. However, the derivative will have an undefined value. So with this in mind, then, we are going to take a look at a couple of examples and check and see how we can determine the min and the maximum values of a function at points where the derivative exists or the derivative doesn't exist. Let's start with example number 2. So what we have in here is the function f of x equals x plus 2 to the power of 3. We have to determine all critical numbers and classify them as min, max, or neither. So to find the critical numbers, we're going to start off by determining the derivative. So the critical numbers will be wherever the derivative is 0 or we said the derivative doesn't exist. So the derivative of x plus 2 to the power of 2 over 3 would be equal to, remember we're using the power rule here that states that the derivative of x to the n would be nx to the power of n minus 1. So what we have in here is 2 over 3, x plus 2 to the power of 2 over 3, subtract 1. Let's simplify some more. So that would be 2 over 3, x plus 2 to the power of, so take away 1 means that you have to subtract basically 3 over 3. So that will make it negative 1 over 3. Now recall that here we have a small little chain. So that means we have to take the derivative of the inside function, but since the derivative of the inside is 1, right, multiplication by 1 won't change the value of the derivative. So let's simplify this a little bit more. So we'll say that f prime x would be equal to, We want to write the derivative in the most simplified form because we are preparing to study the sign of the derivative. So x plus 2 to the power 1 over 3. Now, in order to study the sign of the derivative, we need to take a look at the signs of the numerator and denominator. So numerator is equal to a constant number, so numerator equals 2. It's a constant number greater than 0, which means that it won't change the sign of the entire derivative. So the denominator, on the other hand, is 3x plus 2 to the power of 1 over 3. So we're going to set this equal to 0 to find the values of x that can make the denominator 0, so that we'll be able to study when this expression will be positive and when negative afterwards. So if you divided both sides by 3, then we get x plus 2 to the power 1 over 3 equals 0. Bring both sides of the equation to the power of 3 so that we can eliminate the power of 1 over 3. So that will give x plus 2 equals 0, which tells us that x equals negative 2 will be the 0 of the denominator in the derivative. In the meantime, we're going to say that this is also a restricted value, so a restriction of the derivative of f prime. So in other words, f prime at negative 2 doesn't exist, so is undefined. When you look at the equation of the function, on the other hand, f of x, right here, we're going to say that the domain for f of x is any real number. The way we like to analyze it is this. So as you can see, we have a rational exponent, which makes it a little bit more awkward to kind of identify the domain of right away. So when I am dealing with an equation of some function that I've never seen before, so it doesn't belong to any of the groups that I have studied, what I do is I try to substitute the x value by a positive and see if I'm able to evaluate the expression. So if I have a positive number here, then the entire expression inside brackets will be some positive number. We can bring any positive number to the power 2 over 3, so x positives are part of the domain. Next, I check for the value of x being 0. So if x equals 0, then the value of the expression here will be 2. 2 to the power 2 over 3 exists. And lastly, I will check and see if x equals some negative numbers. So let's say negative 100. So if x equals a negative number, then we know that the value of the expression inside the brackets here would be negative. And if we have a negative number raised to the power of 1 over 3 and then squared, then we're going to say that we can cubic root a negative and then square it. So you can use a calculator as well, so you can do this a bit faster. Therefore, we're going to say that the domain for the function would be any real number x, whereas the domain of the derivative is restricted at x equals negative 2. So therefore, we're going to say that x equals negative 2 is a critical point, and we are going to place x equals negative 2 on the number 9 and start studying the chart. Use the chart to study the sign of the derivative. So here is negative infinity, here is positive infinity. And the derivative is 2 divided by 3 x plus 2 to the power of 1 over 3. At x equals negative 2, the derivative will be undefined because it's a restricted value. So for x values less than negative 2, so you can substitute, let's say negative 3 in here, we'll have a negative value for the expression in the denominator, positive in the numerator, so that will give the derivative a negative sign. On the other hand, for x values greater than negative 2, for example, if x is 0, that's a number right here, for example, the value of the denominator will be equal to a positive number, so positive over positive is positive. So for the behavior of the function, then we'll say that the function will be first decreasing and then increasing. The derivative is undefined. However, the function is not undefined. So the function is defined at x equals -2. And since the behavior is changing from decreasing to increasing, and the function is defined for any real number x, remember this is the function that we are discussing, x plus 2 to the power of 2 over 3, then we'll say that the function will hit a minimum. So the restrictions on the graph of the function are none. So we're going to say x is any real number. The restrictions on the derivative of the function, there is one. So we're going to say x is any real number with an exception that x cannot equal -2. So what is going to happen to the graph of the function at the restricted values? Let's take a look at Desmos and let's draw the graph of this function. So we have y equals, open brackets, x plus 2, close brackets, to the power of 2 over 3. So as you can see in here, the graph of this function will present a cusp at x equals -2. And I'm going to take a picture of this so that we can have it all in our notes. Here we go. And we can take notes on the graph as well, so it's easier this way. So as you can see in here, the function is defined at x equals -2. The derivative is undefined, and the reason why is because if you were to draw a tangent line exactly at x equals -2, the tangent will have an undefined slope because it's vertical, right? Vertical line. So that means that the derivative doesn't exist. So the shape of the graph at the restriction will be that of a cusp. So we're going to say in conclusion that when the derivative of a function is restricted at a specific point, but the function isn't, then the graph of the function may have a cusp at the critical point, and that can happen when the slope of the tangent is undefined. Or in other words, the derivative undefined at the critical point. So, and the function will present either a cusp or a corner. So in the same way, you can reason about the next example. So this is an example for you to try. I will take this up in the next video recording, lesson recording. Well, as always, thank you for learning with me and have a wonderful day. Bye for now.